Hi everybody, I am Firyuza Yanchilina. My presentation is experiments with lasers that will help to refine the value of the Hubble constant. I'd like to tell you about a new experiment which has never yet been conducted or even discussed. This experiment can change our knowledge about the universe. We hope this presentation will interest researchers in the field of high-precision measurements to conduct the experiment. At first, I will tell you a little bit of the theory, and then I'll move on to the description of the experiment. Imagine two galaxies. They're at the same distance from us. The first galaxy is moving away from us at speed v. The second galaxy is stationary. Its speed relative to us is 0. According to modern astrophysical ideas, the redshift in the spectrum of any galaxy is determined only by its velocity. This means that the spectrum from the receding galaxy will be shifted to the red end, and the spectrum from the stationary galaxy won't. In our opinion, this is not the case. We believe that the spectrum of a stationary galaxy will also be shifted to the red end. This shift is approximately 3 times less than the shift in the spectrum of a moving galaxy. Our universe is expanding. This means that in the past, the size of the universe was smaller and its density was higher. Therefore, the gravitational potential of the universe was lower than now. In other words, the gravitational potential of the universe, phi sub u of t, increases over time. It is due to the expansion of the universe. According to general relativity, the radiation frequency of an atom omega depends on the magnitude of the gravitational potential. The higher the potential, the higher the radiation frequency of an atom. This effect is called gravitational redshift, and it has been confirmed in many experiments. This means the radiation frequencies of atoms will also increase as the universe expands. Therefore, in the past, atomic frequencies were lower than now. Suppose we are looking at a distant galaxy. In this case, we see light that was born many millions of years ago. In the past, atomic frequencies were lower than now. Therefore, in the spectrum of the galaxy, we will see a gravitational redshift caused by an increase in the gravitational potential of the universe. The farther a galaxy is from us, the more its spectrum shifts to the red end. This effect of the gravitational redshift must be observed in the spectrum of every galaxy as an additional effect to the Doppler effect. Consequently, the redshift z sub 0 observed in the spectrum of a galaxy consists of 2 parts. The first part is a Doppler redshift z sub v caused by the speed of the galaxy v. The second part is a gravitational redshift z sub phi caused by the growth of the gravitational potential of the universe. The value of the Hubble constant is determined as the ratio of the recessional velocity v of the galaxy to the distance r to it. Astrophysicists put the observed redshift z sub 0 times the speed of light c instead of the galaxy speed v. In our opinion, this is an incorrect equation. The correct equation is equation 3. It is because the observed redshift of each galaxy, z sub 0, contains a non-Doppler redshift z sub phi. To find the Doppler redshift z sub v, we need to subtract the non-Doppler redshift z sub phi from the observed redshift. According to modern data, the Hubble constant h is equal to 70 kilometers per second for each megaparsec, and the age of the universe t is equal to 13.7 billion years. According to our calculations, considering the non-Doppler redshift in the spectra of galaxies, the Hubble constant h sub 0 is equal to 47 kilometers per second for each megaparsec, and the age of the universe t sub 0 is equal to 20.5 billion years. To find out the exact value of the Hubble constant, we propose to measure the non-Doppler redshift of galaxies in a laboratory experiment. In 1929, John von Neumann theoretically substantiated the possibility of creating a perfect mirror that reflects light perfectly, that is 100%, and doesn't transmit or absorb it. About 10 years ago, such a perfect mirror was created at MIT. Using such mirrors, we can conduct an experiment to measure the expansion rate of the universe at an Earth laboratory. So the experiment. A high-stability laser beam passes through a semi-transparent mirror, which splits the beam into two beams. The first beam is directed to a system of mirrors, moves between them for some time tau, then it's directed to a comparator. The second beam is immediately directed to the comparator. The comparator compares the frequencies or wavelengths of two beams emitted from the same source but at different times. The frequency of the first beam will be lower than the second beam because the first beam was emitted from the laser before the second beam. The expected redshift effect increases linearly with increasing time delay tau and reaches a value of 10 to negative 15th power after about 20 minutes. We made calculations and got the next equation. Here, Z of tau is the experimental observed redshift between two beams depending on the time delay tau. H is a modern value of the Hubble constant, calculated from the assumption that the redshift in the spectra of galaxies is caused only by their recessional velocities. H sub 0 is the corrected value of Hubble constant, considering the non-Doppler redshift in the spectra of galaxies. Experiments in space. The non-Doppler redshift effect can be detected during high-precision spacecraft navigation. We sent a radio signal from the Earth to a spacecraft. The spacecraft receives this signal and retransmits it to the Earth. On the ground, the return signal is received and retransmitted to the spacecraft. This procedure is repeated many times over a long period of time. The return signal frequency changes after each cycle. The change in frequency is caused mainly by the Doppler effect due to the moving of the spacecraft. Additionally, the change in frequency occurs due to the growth of the gravitational potential of the universe because of its expansion. The second effect is very small, but it will grow continuously. As the experiment is carried out, the accuracy is in determining the location of the spacecraft, and its speed will increase. This data and data from other similar experiments with spacecraft will help to measure the non-Doppler redshift effect more accurately. The same experiment can be carried out differently. The signal repeater is installed not on the spacecraft, but on the surface of the moon. By conducted experiments in the laboratory or in space, we will find out the magnitude of the non-Doppler redshift effect present in the spectra of galaxies and in navigation signals. This information will change our knowledge about the rate of expansion and the rate of the universe, increase the accuracy of navigational measurements in deep space, and make it possible to find out the value of the gravitational potential of the universe and the rate of its change. You can find the corresponding equations in our article, Experiment with a Laser and a Mirror to Accurately Measure the Hubble Constant, published in the journal Modern Physics Letters A. Thank you for listening to me. Please ask me any questions in chat or by email.